My name is Alexander Charnovsky. I am professor at the Department of Chemistry, Bowling Green State University. I'm a physicist, and moreover, I'm ultra-fast spectroscopist. We look at the ultra-fast chemical reactions and ultra-fast Fret-induced processes. Ultra-fast processes, they occur in the nick of time, very, very fast. So I'll show you in the lab how we look at this process. So then we are in the higher laboratory for kinetic spectrometry. So chemical reactions, as you know, they can be very slow, but then they consist of many steps that are very, very, very fast. It's simply one step that makes them slow. So what we're learning here, how fast the chemical reactions are, what determines the speed, so how quick these elementary steps. So to trigger molecules, we use ultra-fast flash of light. So it's much faster than it takes your eye to blink. The eye blinks on a time scale 0.1 second, and this flash of light is on a time scale of molecular vibration 10 to the power of minus 13 seconds. So then, following this flash, the molecules are synchronized and they start doing the same thing. They start to vibrate, then they go bond breaking, bond making, and so on. And we follow the ultra-fast pulse that triggers the reaction with another pulse that follows elementary steps of the reaction. And we look at the change of the color of the second probe pulse, we call it, as a function of time. So what molecules, what molecular action the probe pulse sees at this time after the trigger pulse, at this time, at this time, at this time. So we are mapping the development of a chemical reaction at this time. So in other words, we are making molecular movie. The laser itself, well, is monochromatic. It gives only one color. I don't know if you can see it, red. We generate what's called white light continuum. White light continuum is very fancy. You will not see it, but believe me, this is a very unintense red light here, okay? Monochromatic. But then we focus this red light onto this crystal. And then after this crystal, we have a bunch of colors. If you can turn off the light, so this is a switch, you can see it better. It's a beautiful ring.
So what Dr. Charnovsky is saying is that the laser which is focused through a chemical crystal incites a reaction. Like he said, this reaction occurs so fast that it appears to repeat continuously. The laser light, after starting the reaction, interacts with each step of the reaction, and that is what is causing the diffraction pattern that you see. The shifts in diffraction angles and frequencies can be used to calculate the steps of the reaction, and this means that the pattern you see can be used to basically create a movie of the chemical reaction that causes this pattern.
After seeing this, Nick and I had one question on our mind. What else can he do with that laser? We had no idea, so we asked.
This laser is an ultra-fast laser, meaning that the pulse duration of this laser is exactly the same as a time scale for molecular vibration, 10 to the power of minus 13 seconds. So the intensity is the ratio of number of photons present in the pulse divided by pulse duration. Pulse duration is 10 to the power of minus 13 seconds, so then the ratio is a very big number. So therefore the intensity is very high, and then the intensity is so high that if the laser pulse is focused into the air, okay, we have to turn on the light. So then the electrons leave the air molecules under the strong perturbation by electric field of the laser light. So what you see here is a little plasma.
Hold on. Did you catch that? He said plasma. That's the fourth state of matter. He used the focused laser to create a little spot of plasma suspended there in the air.
This plasma is due to electrons that were ionized from air molecules, and then they emit as they recombine back. So this is the point of highest intensity. So if I place a card here at this point, then we produce a very big sound. That's card burning. You see, lots of burning. It's not good for the optics.